also thank Gerard for all his contributions to physics, for creating this modern world of theoretical physics in such a wonderful way. Congratulate him again for his work. It's very well deserved Nobel Prize. So this talk will be mainly a review on some things that many people have been working on, and that involve black hole entropy and how we use notions of black hole entropy to analyze the black hole information paradox. Towards the end, we'll describe some recent things. If I don't get to it, you can see some of this in Ahmed Almeri's talk in the Strengths Conference, which is going on right now. The outline of this talk is I'm going to review various ideas about black holes, so how we think of black holes as quantum systems. We are going to review the taxonomy of black hole interiors. We'll discuss various notions of entropy. We'll discuss a new entropy formula, well, relatively new, about a few years old, but of course, I think it's not widely appreciated how interesting this formula is. So we'll discuss this formula. We'll discuss the full quantum version of the formula, and we'll use it to black hole problems towards the end. So there is a central hypothesis that has been applied to the study of black holes. And the idea is that a black hole as seen from the outside should be the same as some quantum system. And so this quantum system is supposed to have a number of qubits, or degrees of freedom, of order the entropy, or the area of the black hole. And not only that, but also when the black hole is viewed from the outside, the black hole should evolve according to unitary evolution. So this is the hypothesis that quantum mechanics is reserved by black holes, and it's contrary to the hypothesis that black holes lose information, as Hawking had said. So this is the alternative hypothesis, and this is the central idea or central hypothesis in what we are going to discuss later. Now, what's the evidence that this hypothesis is correct? One evidence is the entropy counting from string theory, that we can find very special black holes in very special theories, and then using strings and difference, we can reproduce the entropy given by the area formula. Another reason is the duality between anti-de Sitter space and conformal field theories. Using that, we can describe the black hole and everything that happens around the black hole in terms of a theory that lives on the boundary. So we have on the boundary, we have a theory of strongly interacting particles, and that's supposed to describe any experiment that we can do in the interior by sending particles into the black hole, so bulk particles into the black hole, and the black hole evaporating and sending those particles back out. Okay. Now, there are a few things that are sometimes that I would like to emphasize about this hypothesis, is that this is a statement only about the black hole as seen from the outside, and talks about the experiments that you can make from outside the black hole. So you stand far from the black hole and do experiments. As an analogy, maybe I should say, imagine that you are trying to study what you see. You're trying to study ships moving in the ocean, but you stand from the shore on a solid platform, and then you describe the ships. We'll later discuss what happens when you are in the ship and you are moved by the waves, and maybe you might be behind the horizon. And yeah, so that's we haven't made any statement about that yet. Okay. Now, what about the inside of the black hole? So, what about the region behind the horizon? Now, as any development in science, the first thing you do is you collect specimens. Okay. So, like we are like Darwin collecting birds in the Galapagos Islands. We just collect the kinds of birds that there are, and then we'll try to discuss some theory that describes all these birds. So the simplest interior is the one that arises when the black hole is made from collapse. So we have a star, the black hole collapses. This is the Penrose diagram, and in this situation we have a horizon. This is the outside of the black hole, and we have an interior. So there is just somehow single interior vision. If you take a spatial slice that surface, this special slice, it has the topology of a three-dimensional R3 Euclidean space. So there is some sphere far away that, as you go to the interior, shrinks, and it contains all the matter that's been falling into the black hole throughout its history. Now, this is not the only possible interior. So this is the interior that we can easily, well, that is made in our universe naturally when a black hole collapses. But there are other interiors that are allowed by Einstein's equations. And we will collect on these specimens. So we'll discuss these other interiors also. How to make them is another story. Some of them can be made through more complicated processes. But let's just discuss solutions. These are all consistent. What I'm going to discuss are all consistent solutions of Einstein's equations plus matter. So the other one, the first one, and we're going to mention basically the ones that pose some paradox for attempts at interpreting the interior. So the first one was the so-called bag of gold. So this is a space-time where a given, let's say, initial slice, t equal to 0 slice, has this kind of topology or geometry. So we have R3 far away, and then we have a small connecting region, and then we have a huge sphere that we can think of that as the initial slice for an FRW universe, a closed FRW universe, with some matter in it. Now, the reason that Wheeler was discussing this is because we can put lots of matter in this universe, and the amount of matter we can put is unbounded. We can make this universe as big as we want. And so in some sense we can have lots of entropy inside the black hole, and entropy which is bigger than the area of the horizon that will eventually form. So this, I should have said that this is the initial slice for the universe, and then as you evolve it using Einstein's equations, you find that the black hole forms outside with a relatively small area, and then the interior looks like an FRW closed universe with a black hole in it. Okay, so that's the later time evolution. But the reason that he proposed this is that this is a counterexample to the idea, or an apparent counterexample to the idea that the entropy of the black hole, that the area of the black hole counts the entropy of everything that can be inside the black hole. Okay? So if you think that the black hole entropy is capturing that entropy, then this would be a counterexample for you. Now, the Wikipedia article says the holographic principle is supposed to solve the black hole information paradox, but there exist classical results, so it talks about this as a counterexample. And we'll discuss how this Wikipedia article is updated. But for now it's a problem, so it's a correct statement. Then we have an evaporating black hole made from collapse, so this is a slightly more developed version of the previous one. So here the black hole collapses, and then it emits Hawking radiation. And so from the point of view of the outside, the black hole eventually disappears, right? So at very late times, we should have the same Penrose diagram that we have for a flat space, which is this one. And here we are assuming that, well, the final stages of black hole evaporation are not a big change to the geometry that we derive classically, so it's something quick happens and that we don't know, we can derive from Einstein's equations. And so if you assume that, you get this type of diagram. So in this type of diagram, you have Hawking radiation coming out here in the future, and here the late time, some slice close to the singularity, we have all the partners of Hawking radiation going into the black hole. And if you look just at the outside, it looks like you can forget about this, and then you will have the situation where a pure state seems to be going to a mixed state. Okay, that's the black hole. That's the Hawking information paradox. And this situation is somewhat similar to the bag of gold example that we discussed, in the sense that if you look at the black hole at some very late time t, so t is a very late time. By late I mean that the black hole has evaporated to a size which is much smaller than the initial size. So the entropy of the black hole is, the entropy given by the area of the horizon is much smaller than the initial entropy. But nevertheless, the entropy of Hawking radiation is comparable to the initial black hole entropy, so it's much bigger. And for the same reason, the entropy of all the partners here, which are entangled with this one, will also be much bigger. Okay? So it's much bigger than the area of the horizon. So we have a situation similar to the bag of gold. We have the structure of this spatial slice, the green slice here is similar to the previous one, same topology of almost similar geometry of R3 far away, then there's a neck, a small neck, and then inside we have lots of entropy. And it closes off smoothly here at R equal to 0, with lots of entropy bigger than the black hole, bigger than the area of the horizon at this time. Okay, so now if you make the hypothesis that the black hole evaporation is unitary, the central hypothesis that we discussed, then if we look at the entropy of outgoing radiation, we expect something interesting. So Hawking's prediction is that the entropy of the radiation starts increasing. So as the black hole starts emitting radiation, this radiation is thermal and it has an increase in entropy. And eventually the black hole evaporates completely and it emitted some entropy which is in the order of magnitude of the original black hole entropy. It's not equal, but it's a little bit bigger because the process is not reversible. So on the other hand, if you expect unitarity, you would expect that if you form the black hole from some pure state, that entropy should go back to 0 by the time that the black hole has evaporated completely. And so from unitarity, you expect that the entropy should decrease all the way back to 0. And so this is what you expect, and you would like to have some rules or some way of calculating this entropy from the point of view that reproduces this code. I haven't got it. Okay, so that's so now let's continue with the idea of the taxonomy of black hole interior. So another solution is the Schwarzschild solution, the original Schwarzschild solution. The first solution was written down, non-trivial solution of Einstein's equations. And this solution has two exteriors, two black hole exteriors. Okay. So it looks like, so this region here is like a black hole exterior, this is another black hole exterior. This surface sometimes is called the Einstein-Rosen bridge. And it took many years to really understand the geometry of this solution. It's kind of surprising how confusing it was historically. And so it's also taken many years to, we're still understanding the quantum version, quantum interpretation of this solution. Now this solution exists whenever you have a near extreme black hole. It would exist also with asymptotic ADS boundary conditions, so we have a similar solution. But now this idea of the decentral hypothesis, hypothesis, remember, is that a black hole seen from the outside should be described by a quantum system. So this black hole has two outsides, so it should be described by two separate quantum systems. Okay? And so the idea here is we have two boundaries or two exteriors, and we should have two separate quantum systems describing this whole configuration. And so the idea is that this black hole should be interpreted as an entangled quantum system. So we have whatever qubits we're describing a single black hole, we have the same qubits describing this black holes as seen from the outside, and the only peculiar feature about this one is that they are entangled. They're in a particular quantum state, they're in a particular combined state of the two quantum systems, and that particular nature, which is this particular quantum state, is that we have all the energy eigenstates of one system, you entangle them with the other system using these thermal looping factors, and that is supposed to generate this geometric connection that we see in the geometry. And we think, with Lenny, I think Lenny already talked about this, so I won't dwell about this, but we thought that this would be a more general story, and we'll discuss that later. Now, all of this, so we saw a bunch of insights, and we discussed how black holes from the outside look like quantum systems. But the question that we're going to try to address now is how this quantum system is related to the inside. Okay? And before addressing, I will not give you a full answer to this question, but we'll see some indications of at least what region of the inside is described by the quantum system. Okay? And before addressing this, I will have to talk a bit about a concept that's been very useful, which is this concept of gravitational entropy. Okay? Now, even before talking about gravitational entropy, we should realize that for systems in general, there are two notions of entropy that it's very important to distinguish in this context. So the first notion is the notion of coarse grain entropy, or thermodynamical entropy. This is the first notion that you encounter in your courses on thermodynamics. This is the entropy that obeys the second law, even for an isolated system. And well, it has its own definition. It's coarse grain, so you maximize for all possible density matrices that agree with your observations, etc. And then there is the notion of fine grain entropy, which is the actual entropy of the system. So it's your actual ignorance. So if you have a density matrix for a quantum system, you just trace row of that density matrix you actually have. Okay. While the coarse grain entropy is the trace row of the system that maximizes the entropy subject to the condition that all the simple observables agree with the observables you have for the density matrix you actually have. Okay. Are these two notions of entropy clear for everyone? Or? Yes, I hope it's familiar. Yeah.
How can you even assume that there is such a difference?
Well, okay, let me tell you an example where there is a difference. So imagine that we have the gas in this room, right? So we normally would assign it some entropy, right? And that entropy is typically what we call the coarse grain entropy, because the gas in this room could have started with all the molecules in the room sitting in one corner. So that would be a state with very low fine grain entropy. But then it evolves just by unitary evolution without coming to the outside to the state of the gas we have in this room. And so in that case, the fine grain entropy would be much smaller than the coarse grain entropy that we would have at late times for that initial state.
But still, your fine grained entropy, if you have no coarse graining at all for a pure state, it's just zero. It's zero for Neumann.
Yes. This is that's important. This would be an important part. Yes.
That is a pretty useless question. The pure quantum state thermalizing has, of course, always this fine grain entropy zero. And
Yes, that's right. You're absolutely right, and this is important for what we're going to discuss. Yes. Yeah. So I'm glad that you brought this. So. But we could also have started from a density matrix, and then the fine grain entropy should not be zero. And so if we have the gas in this room, we could have it, let's say, in a pure state, or we could have it in a mixed state, and it would look, from the macroscopic point of view, would look similar. Yeah.
So you mentioned in describing one of those, ignorance.
Yeah.
Is it your belief that entropy has anything to do with what we know?
Well, this is the definition, and this is the formal definition of entropy.
No, the Boltzmann entropy doesn't have anything to do with what anybody knows. The von Neumann entropy has nothing to do with what anybody knows.
I'm not sure I understand the statement. This is just the definition using the mathematical formulas.
The Shannon entropy has nothing to do with what anybody knows.
Well, I'm using this definition for.
Okay.
I don't know. I think this is the conventional definition. What that translates into English, I'm not very good. What is the thermodynamic black hole entropy? So the idea is that the first point is that the entropy given by the Bekenstein formula is the area of the horizon. That is coarse grain entropy. So that's the first point that is important to appreciate. And it cannot be otherwise because the area of the horizon increases. Okay, so it can increase when you form a black hole and so on. The area of the horizon increases, and the entropy that increases is the coarse grain entropy. So if it is any entropy, it can only be the coarse grain entropy. That's the first point that I hope is clear to everyone. Well, it's not 100% obvious that there is any coarse grain, any system for which this entropy applies, but if it is one of the two entropies, it's the coarse grain entropy. That should be clear. Now, the question is whether there is any formula for fine-grained gravitational entropy. And one main point I want to convey in this talk is that there is a formula for, there is an area formula for fine-grained entropy. And it's the area of some other surface. It's not the area of the horizon, it's the area of some other surface that we'll define in a second. And so this is a new development in the last maybe 10, 15 years. And a version of this was originally proposed by Ryu-Takayanagi, and then developed more by these three people, Ryu-Takayanagi and Takayanagi. And what we do now is just define what this notion is. And so the idea is that you have to look at an area, but an extremal area. So it's in some sense a minimal area. So imagine that, so this area is found as follows. So imagine you surround the black hole with a surface, right, with a two-sphere, special two-sphere. It's a codimension two-surface in space-time, so it's a two-sphere. And then you start shrinking this two-sphere as much as possible, so you find a minimal area. And you're allowed to go inside the black hole. So you take this two-sphere, you don't stop at the horizon, you just continue inside, and if you can continue shrinking, you shrink it, until you find the minimum size. And that minimum size will be, that area will be the fine-grained gravitational entropy. So that's the hypothesis. And treat it as a hypothesis if you've never seen it before. But this hypothesis follows from the rules of ADS-CFT. So in situations where you have asymptotic ADS and so on, you can argue that if you believe in the ADS-CFT duality, then you should also believe in this formula. It follows from the same kind of rules.
But what means that you shrink it as much as possible? You cannot shrink it completely?
You can in some cases. So we'll discuss now different examples. Yes. So let's go back to the different interiors, some examples of the interiors we have. So for example, in the case of the black hole that was made from a pure state, we start from some, so here in this Penrose diagram, each two-dimensional surface is a point, right? It's a point on this diagram. So there are two directions that we haven't shown here. And so that's the surface outside the black hole. And now we shrink it, and we can shrink it all the way to zero, as you just done. All the way to zero, and we get that the fine-grained entropy is zero, as you pointed out. Right? So in this case, we get a result from gravitational entropy that agrees with what we expected. So there is actually a rule for how you pick the slice in the time direction, but I want to discuss it. I'm making a simplified explanation of the Ryu-Takayanagi formula. Now let's consider now the two-sided black hole. So we start from one exterior, and we start shrinking the surface. And famously, this Einstein-Rosen bridge has some asymptotic R3 geometry, and then has a minimum at some distance, some area, and then it expands on the other side. So if you follow this prescription, you will find that the minimal area is at this point. Okay? And so in this case, the fine-grained entropy is equal to the area of the horizon. Right? So we have this other situation. Now I should point out, I should emphasize that here the area of the horizon grows, right? And it's non-zero. So this is a situation where the fine-grained entropy is smaller than the coarse-grained entropy. And just by the definition of the two quantities, it's always true that the fine-grained entropy is smaller than the coarse-grained entropy. So the maximum it could be is the same as the Beck-Einstein formula. And in this case, we saturate that maximum. So we have the same as the Beck-Einstein formula. And there are also some intermediate cases where you have some kind of, so the intermediate cases always contain some kind of wormhole that connects the two regions, and where the area shrinks and then expands again. That's some other side, but it might shrink to some value smaller. So there could be wormholes which, so in this wormhole the two exteriors are directly touching each other. There could be longer wormholes where they don't touch each other directly. Maybe Lenny talked about those. Now, if you have never seen this formula before, you should be surprised and somewhat skeptical. Okay. I was a bit skeptical myself, and it took me some years to understand this and the implications for this, and the same might happen to you. But there were many checks of this idea. It passes many non-trivial checks. This formula, this prescription, obeys some highly non-trivial formulas for entanglement entropy in quantum systems, called, for example, the entropy subadditivity formula. It's really, so there is a lot of evidence that it's true. It's somewhat proven from the rules of ADS-CFT, but we want to apply it in general. So treat it as a hypothesis similar to the hypothesis that Beck-Einstein had, that the black hole entropy is given by the area of the horizon. So now we have a new notion of a black hole entropy. Now, it's been known for a long time that these two notions of entropy that we just, well, at least the Bekenstein notion of entropy is not the full answer, and we need some correction. So when we are talking about the quantum theory, just even perturbative quantum theory, but it's understood what the correction is. It's just simply, and actually the correction it was understood from the very beginning, from the first time that Bekenstein formulated it, essentially, because the full thermodynamic entropy of the black hole as seen from the outside should include also the entropy of the matter fields outside the black hole. And we should treat this together. That's the full entropy from the outside. And in quantum mechanics, it was pointed out by this gentleman that in quantum mechanics, there is a contribution from the quantum field. So even if the quantum fields are in the vacuum, when a black hole, let's say, forms, when you cut this vacuum state into two parts, the exterior of the black hole and the interior, then there is some entanglement in the vacuum, just in quantum field theory, and that gives rise to an entropy, and quantum contribution to the entropy from the quantum fields of the vacuum. Okay? That's sometimes called entanglement entropy contribution, but we should think of that more properly as the von Neumann entropy of the fields outside the black hole. So this von Neumann entropy of the fields outside counts both this vacuum contribution, or even if we have ordinary entropy of matter, like we have an accretion disk around the black hole, that is also included. So then that's sometimes called the generalized entropy formula, so the area plus the quantum contributions. And it's been recently, well, relatively recently shown that this entropy really obeys the second law of thermodynamics, and we use this again using some interesting formulas for this entanglement contribution. And so, for example, processes like the black hole evaporation, which decrease the horizon area, increase the entropy of the fields outside in a way that is such that this second law is obeyed, right? So the entropy of the fields outside increases by more than the area of the horizon shrinks. So it's a non-trivial statement. But so that's, yeah, was there a question? Okay, so now the question is how should we modify this fine-grained notion of entropy? And the idea is that again you add the entropy of quantum fields, and there's been a further hypothesis that in this extremization process you don't extremize the area, but you extremize the area plus the entropies of quantum fields outside. Okay. So that's the final formula. So that's the formula we're going to explore, and that's the formula that is conjectured to be correct. Okay. And there is this formula passes again some non-trivial checks and leads to surprising, interesting conclusion. The surface that extremizes sometimes is called quantum extremal surface. This is just the name, so that's the final surface that results from this process. And associated to this, there is a notion of so-called entanglement wedge. So that's the region that is outside the, that is swept by this. So if you start from far away from the black hole and you do this minimization process, there is a whole region that is left outside this final surface that you find, and that region is called entanglement wedge. This is just the name for this. And many people explore this. So let me try to, again, explain what this is. So we have, this is a picture of the same process that we were doing before. So we have a surface around the black hole, and we are counting the area plus the entropy of all the fields that are outside. So this is the region outside. And then we shrink this until we find the minimum contribution of the sum of the area plus the entropy of the quantum fields. The minimum, in general, will be inside the black hole horizon. So we did that for for the case of the wormhole. We will find the entanglement wedge would be this, and here you see it's kind of a wedge. That's part of the reason it's called entanglement wedge. If we did that for a black hole that forms from collapse, it would become the whole black hole geometry. Okay, so we saw that the first hypothesis that we made was that there is a quantum system that describes the black hole as seen from the outside. And one question is, what portion of the space-time does this quantum system describe? Does it describe only the outside? Does it describe a portion of the inside? And if so, which portion? So now we'll introduce a new hypothesis. And this will end the number of hypotheses that we introduced. We had 3. The first central one was the fact that black holes are described by a quantum system. The second was the notion of fine-grained entropy. Well, 1.5 is the Hawking-Bekenstein formula. And the third one is this entanglement wedge reconstruction. So this is the idea that the quantum system that describes the system from the outside describes everything that is included in the entanglement wedge. Okay? And this reconstruction depends on the particular state of the quantum system. And there are some arguments for why this is the case. I will not go over them, but I should from the outset say that there is no explicit construction that given a bulk state gives you some state in the quantum system. So for example, in the context of ADS CFT, where we have an independent description of the quantum system of the black hole as seen from the outside, there we would like to have an explicit embedding between or relationship between the two, but we don't have an explicit construction. So this is treated as a hypothesis. Notice, well, one important point is that that is evidence for this hypothesis, is that if you change anything in the entanglement wedge, like you add a little bit more entropy and so on, the final entropy, the final fine-grained entropy will change. Okay? So this shows that, and that's the fine-grained entropy of the quantum system that describes the black hole. So that is some evidence that everything that is within the entanglement wedge is described by the quantum system. Okay, so I should emphasize that the notion of fine-grained entropy is a notion that is defined in that quantum system that describes the black hole as seen from the outside. Right? That's the home of this notion. Now, what we'll now argue is that this removes some apparent paradoxes. Okay? So we'll go over some apparent paradoxes and see how these hypotheses remove them. First, let's start with the bag of gold paradox. So here, an important point that is central is that this notion of entanglement wedge depends on the entropy that is contained in the system. Right? So when we have the bag of gold, we could have two situations. We could have this big space-time, but let's say it's in a pure state, or we could have a big space-time in some state that has a lot of entropy. Now we can have the same system with the same, let's say, stress tensor, but different entropies. So for example, we could have two galaxies, and if the two galaxies are entangled with each other in a pure state, then we would have this situation where we have low total entropy. If they are in a mixed state, then we would have this situation with a large entropy. Okay. Now, what this prescription says is that the following. So we are supposed to minimize the area plus the entanglement entropy. So we start from the picture on the left. We start with an area far away, right? It shrinks to a minimum, then it expands a bit more, and then it shrinks to 0 in the interior. Okay? And since the entanglement entropy, since the entropy of the fields is relatively small outside, that's the true minimum. So the true minimum is something close to 0. Okay? In this situation, we start with the same thing. We have a surface that goes to a minimum, but if we try to unwrap that surface by going into the interior, we would catch all the entropy of the fields outside, and that would increase the entropy. So if we had the surface at the very minimum, we would have a much bigger entropy due to the contribution of the fields, and therefore the true extent of the entanglement wedge as seen from the exterior would stop here, and in this case it would continue all the way in. Okay. So we don't run into the paradox that Wikipedia explained. Okay, so this is the solution to the Wikipedia question. Now, it is important that the size of entanglement wedge depends on the entropy of the fields inside, not on the energy. Right? So we would have the same. Well, I've already made this point, but to emphasize it again. So now we consider another problem. And I should point out this argument was made by Wall before we put in the reference, by Aaron Wall. Then we have the old evaporating black hole. So now there is a recent paper, two recent papers, one by the first four authors and the other one by Princeton. And what these papers did is they applied this notion of entanglement wedge for the case of an old black hole. So here we're imagining we have an old black hole that evaporates, and in order to define these concepts perhaps most sharply, it's convenient to somehow separate the black hole from the bath or the exterior. So here I've assumed in drawing this picture that at this time we uncouple the black hole to the exterior. But well, you could make a slightly more complicated discussion. But the central point that they made is that if we look at we look at this black hole at some very late time when it has lost where the area of the horizon is much more than the initial area, and you calculate this entanglement wedge or fine-grained entropy, you find that the proper surface that describes it is a surface that is here. Remember that when we first looked at this and we looked just at the classical piece, at the classical area, that area was minimized over here and it was zero, right? It was a pure state. But if you look at this at late times, you also have to include the entropy of this radiation here, right? And when you minimize the whole combined system, it turns out that the minimum, the true minimum, is around here. Right? It does not include all of the interior. So that's the central point. And this situation is very similar to the bag-of-gold situation that we discussed before. So I hope the discussion of the bag-of-gold was clear why you have the entanglement wedge different in the two cases. And for the same reason, you have a difference in these two cases. So here, just the evolution just from the bulk physics books, you find that this radiation here is entangled with this sort of the partners of Hawking radiation are entangled with each other. So they have a large entropy here if you only consider the inside, and this is the reason why then the entanglement wedge here is smaller. Okay. So then if you calculate the, so you can make a curve that you can do a plot. This looks similar to the page curve, but it's not quite the page curve. What this is the entropy, the fine-grained entropy of the black hole. Okay, so we're going to make a plot of how the fine-grained entropy of the black hole evolves. So as time progresses, here, so go back to this picture, as time progresses, we're calculating the fine-grained entropy of the black hole as a function of time. And so as time progresses, we have to include, so before we said that the fine-grained entropy was zero when we calculated it classically, but when we include the quantum corrections, we also include the entropy of the partners of Hawking radiation that are here inside. And that entropy then increases as the black hole progresses. Yeah.
When you say late times and the black hole has shrunk much smaller than the initial size, is it still bigger than Planck?
Bigger than Planck. So in this whole discussion, we are bigger than Planck so that we can apply these formulas. So if it is smaller than Planck, then we can't apply these formulas. But the idea is that when it's smaller than Planck, this has low entropy and it's a small correction to whatever we're discussing. An important point is that the turnover in this curve occurs when the black hole is much bigger than Planck area. And so we have, if you continue, so the surface, when the surface is zero, that's one saddle point of the, that's one extremum of the, but it's not the global minimum of the, that when we try to minimize the area plus entanglement entropy, we might find multiple minima, and we're supposed to choose the smallest one. So in this equation, one of the minima is the one which has zero classical area, and there is the other one, which is the one where the surface is over here, and there is a transition between the two when the two become equal, and so the actual minimum, it has a curve like this. And when you calculate the fine-grained entropy using this formula, you find that the fine-grained entropy decreases at late times. Okay, so we find this feature for the black hole fine-grained black hole entropy. If we did the same plot for the area of the horizon, we would find that the area of the horizon starts at zero when the black hole forms, very quickly goes to the area of the initial black hole horizon, and then it slowly decreases. So that would be the plot of the coarse grain entropy. But this is what the fine-grained entropy is doing for the system. And we can ask, what about the entropy of the radiation itself? Because this is not quite the page curve, because the page curve related to the entropy of the radiation itself. And if you assume that the initial state was in a pure state, then the entropy of the whole system should be 0. And so the entropy of the black hole that we showed before should be in principle equal to the entropy of the radiation. And we would get this page curve. But this relies on this assumption that the whole evolution is unitary. Now, the radiation appears to be in a mixed state, and so why does it appear to be in a mixed state? Because it was entangled with the fields that were inside the black hole. Now, how do we know this? So we know this by calculating the evolution through gravity, and therefore we should also use the rules of gravity to compute fine-grained entropy. But we saw that the rules of gravity for calculating fine-grained entropy are a little subtle, right? And so we have to apply those more subtle rules. So I'll try to explain now how to do this. And what we will try to argue is the following. So before we discussed what the entanglement wedge of the black hole was, and it was this region, previously I drew it in green, now this is the entanglement wedge of the black hole. And the idea is that the entanglement wedge of the radiation, so we try to calculate, we look at the radiation and calculate the entanglement wedge. It should include also this region. Okay? So you should disbelieve this. You should not. So if you don't disbelieve it, it's because I'm not explaining it clearly. You should disbelieve it, but I will try to argue for why this should be true. This is a very surprising thing, and I'll try to argue why it should be true. Okay. And so, but I would like to point out that if it were for some reason to include both, so let's just make the hypothesis that this is the right entanglement wedge, then the entropy of the fields, the quantum fields, would be small because this region, these fields here would be entangled with this one here. They would be entangled, and in fact the evolution through the bulk geometry tells us that they're entangled, and therefore their entropy will be small. Okay. So the entropy of the quantum fields is small. If we only consider the outside, then the entropy would be big because we are not crossing this out. That's what Hawking did. But if you include both, then it is small, and that's the quantum fields, but we have to include its area that is small and equal to, it's related to the black hole horizon area. So first I'll give a sort of kind of hand-waving analysis, and then we'll do an analysis which is a little more concrete. So the first one goes through this hypothesis of ER equal to PR. So this is a hypothesis that whenever you have entangled systems, you have some kind of geometric connection between the exterior and the interior. So we have the Hawking radiation, and the idea is that this is somehow connected to the interior through some tiny little wormhole, some kind of geometric connection that we don't know exactly what it is. And then that is connected, those are connected to the interior and those interior Hawking modes. And so when you compute the naive entropy, you are cutting all these wormholes here, and you are not finding the true minimum of the Ryu-Takayanagi of the quantum extremal surface. The quantum extremal surface could be smaller and could be deeper inside the black hole interior. Okay, this is just a picture. We call this the octopus. The name is not good. There are 6, but there are not 8 legs here. But anyway, but now we'll discuss some way of making this picture a little more concrete. And first I will review some aspects of this story that, as they arose originally in ADS-CFT. So this development of the fine-grained entropy actually went through thinking about the area of subregions, in entropies of subregions in ADS-CFT. So I'll go through that in some detail, and then we'll try to give a concrete picture of what that wormhole that connects the two sides is. So this is basically the original question that Ryu-Takayanagi were trying to answer, which was the following. So imagine you have a quantum field theory that is, let's say, defined in one spatial dimension, and the quantum field theory is in a pure state. Okay? And now you look at some region, the region in green, so that green segment that is here. So that's a sub-region of the whole space. And you say, what is the entropy of the quantum fields in this sub-region, the Neumann entropy? Now it turns out that this entropy is non-zero. Okay? That's because in the vacuum state, the fields are entangled between the inside and outside. This entanglement is important for giving rise to Hawking radiation and so on. And, it's an important property of quantum field theory. So they said, well, let's compute this, but let's compute this in a theory that has a holographic dual, so a theory where there is an extra dimension, and the extra dimension, so here is the vertical direction in this blackboard, so it's a curved extra dimension. And what they said is, well, we should find the extremal surface, so we should start with the surface which is that of the green segment, and then we move it inwards to the bulk, and we find the place where the area is minimum. And because the geometry is curved, the minimal area is not just a straight segment, but it's a curved segment of this form. So it's a curved geodesic. So this is just two-dimensional hyperbolic space, and the minimal area or minimal length, in this case, minimal length curves are just semicircles. So this is supposed to be a semicircle. And the entanglement wedge is whatever lies inside. And so that's the story for this case. Now we could have we could repeat the same for two separate intervals. And so we have two intervals that are far away. Then the minimal surfaces are very similar. So that's for well-separated intervals. But now, if the two intervals are closer to each other, then we could have a situation where the true entanglement wedge is given by this other interval, so we can combine these two lengths. So there are two possible surfaces. One is given by the dotted lines, right? So this we could sum the length of these two intervals, or we could find this other length, and it turns out that for close enough intervals, the solid lines here have shorter total length. Okay? So this is somewhat similar to the transition we described before when we were talking about black interiors. But and this is just reflecting the fact that when we have a quantum system, quantum state that is composed of two subsystems, here in this case there are the two intervals, the total information that the state contains is bigger than the information contained in each of the two parts individually. Right? So each system is described by some reduced density matrix of one interval. There is the reduced density matrix of the other interval. But when we have the reduced density matrix of both intervals, that's a different one and can contain more information. Information that captures the information that is contained in the entanglement between the two. And when we have, even in the vacuum state of a quantum field theory, we have this type of transition. And this is something you can check for, well, this is, of course, in theories that have a gravity dual, but you have similar transitions that you can analyze in just in theories that are solvable, like symmetric orbifolds and some simple solvable two-dimensional field theories. You can have a similar transition. In some even simpler theories, like a free scalar or free boson, when you change the size of the interval, the behavior is continuous. There is no sharp transition. It's just continuously goes between these two possibilities. And I guess maybe that's also the way things work in science, that when we use our common knowledge of each person, we talk to each other, and then we can expand our horizons beyond the individual horizons of each person. Now we'll discuss a conformal field theory with a boundary. So imagine that we have a one-dimensional CFD, and there is a boundary, right? So there is a wall that extends in time, and where the field theory ends. And then in that situation, the bulk dual will have an extra dimension, but in the extra dimension we have some end of the world brane, so some brane where the space-time is ending that has its own dynamics, but that's the bulk dual. And then we can again consider an interval that could have this entropy. Now we can, a small modification of this is to consider a boundary system that has a lot of entropy, like a Kondo-like model, for example. And in this situation, this brain that goes into the interior has its own two-dimensional gravity. So in the bulk, we have a three-dimensional gravity theory, but now we also have a two-dimensional gravity theory in this brain. And so this type of system can be viewed from the two-dimensional point of view, can be viewed as two-dimensional gravity, so one space dimension and one time dimension gravity on this surface, coupled to a system that is just living in flat space with no dynamical two-dimensional gravity. Right? So you can think of this as a two-dimensional system that would have black holes and so on, coupled to a conformal field theory. So that's the two-dimensional point of view. And you can think of a two-dimensional gravity system that is coupled to a conformal field theory. And that conformal field theory exists in the part of space that is described by two-dimensional gravity, and also in the part of space that doesn't have two-dimensional gravity, or where the two-dimensional gravity is essentially frozen. This is similar to a black hole that is in flat space, and you have the region near the black hole there, gravity is important, but far away from the black hole, gravity is not very important, okay, because it's essentially frozen. So here we have a similar situation, except that this two-dimensional field theory has a three-dimensional dual. Okay? And the three-dimensional dual is this full three-dimensional geometry that we have here. And now we can use then the rules, just the classical rules of Ryu-Takayanagi to calculate the entanglement entropy. So we can set up a situation where we form a black hole, and then at late times we'll have a picture that roughly looks like this. So we have some brain here, where the two-dimensional gravity lives, and then we have the radiation coming out of the black hole lives in this one-dimensional field theory. And then if you naively compute the entropy of radiation at a Hawking, you would be computing the entropy using this Ryu-Takayanagi surface, and that would have a large entropy. But the minimal entropy would be one where you consider this other geometry, where these lines end on this surface, and that can be, well, in this situation, will have a lower total entropy. Okay. So, and you can view this interior as, well, here this is again a one-dimensional field theory, and by the rules of the game, the radiation here is entangled with the state of the Hawking partners in the interior, and this is a kind of geometric picture of the whole setup that we get through holography, and the whole entanglement wedge is given by this region, and you can view this extra dimension as the wormholes connecting the radiation to the interior. So it's an explicit picture of this wormhole that connects the exterior radiation to the interior geometry. And this is something we are working on with these people, and we haven't published it yet. So, what? We're done. Yeah. So this is. So here I have a summary of this last part that I mentioned. So this is the new part. If the matter has a gravity dual, then the coupling to gravity is similar as in the Randall-Sundrum setup, if you know what that is. And then the whole story, this whole previous story of Pennington and the other people could be said using the standard classical RT formula. And the wormholes connecting the radiation to the interior are completely explicit, and they come just from the extra-dimensional bulk. So in some sense, solving these problems for black holes is not more difficult than understanding in more detail how, let's say, ADS-CFT or gauge gravity duality works in general. I'm not saying that's not difficult. I'm just saying that it is the same problem. So this is a conclusion and summary of the whole talk. So we discussed a new form of gravitational entropy. I hope if you didn't know this formula before that you pay attention to this formula. I think it's very interesting and very important. That gives the fine-grained entropy. It is very surprising, and it's before people used to think that gravity just is some kind of average property of the system, that is a kind of thermodynamic approximation to the system. But this formula shows that this is really wrong, because gravity somehow knows about the fine-grained entropy, so that it's stored somehow through this geometric form of the solution behind the black hole horizon. Now, this fine-grained entropy formula has both a classical piece and a quantum piece, and the quantum piece is important for solving these paradoxes. And then we discussed the entanglement wedge reconstruction hypothesis, which tells us which region we can expect to reconstruct from the black hole exterior by manipulating the black hole microstates. And the final picture gives the right page curve. Now, in the future, we would like to understand how this entanglement wedge reconstruction really works. So we would like to translate this from a hypothesis to a theorem, okay, mathematical theorem, and to understand in more detail how we map the interior observables to states in the quantum system and so on. Okay, thank you.
Thank you. We have maybe time for a few questions. First,
You don't have to look, take it out.
I think actually you do to turn it on.
yes, but I have to switch it on, I thought.
No, I think so.
Can you?
No, I think it's not on.
It's not on, so that's why I have to switch it on first.
Sorry, you're right.
Well, I think I hear the question and I can repeat it.
Yeah, maybe for the recording.
Which of your entropy definitions corresponds to counting microstates?
Well, if you want to count the microstates of the black hole, well, you can use any of them if you interpret it correctly. So if you really want to count the total number of microstates in the full Hilbert space, then it could be the fine-grained entropy, but you need to entangle it to another equal black hole.
But if you modify any of these standard expressions derived from the standard entropy, you would modify the working temperature,
No.
and that would not be allowed. So the number of microstates cannot be much different from the standard entropy.
This whole story does not change 1 iota of the standard discussion of black hole microstates. It really is adding to the discussion. So it's adding, the thing that it adds how we should guides us to how we should interpret the interior. So it's not modifying anything related to the black hole, to the standard entropy counting. So the counting of Schrödinger and Bafa is not modified or any of those things.
The other question is, can you describe a really stationary black hole? That is to say, you take a black hole in a large with finite volume and you look at the energy eigenstates.
Yes. Yeah, you can discuss it. So a black hole that is in a box, for example, where you can define properly the energy eigenstates.
Are they pure states then?
Yeah. You can have a black hole in a pure state. So the idea is that the black hole in a pure state will have an interior, will have some interior that will be quite complex, but that interior will be such that the quantum extremal surface is trivial. So
I still hope one of these days you people will read my papers which show that black holes have no interior.
yeah. So this picture is inconsistent with these ideas. Yeah, with your ideas.
For the discussion session also.
I think the distinction between fine-grained and coarse-grained entropy is conceptually very useful. It avoids some of the confusion. My question is this fine-grained entropy also useful for some practical purposes? You know, you can do the same thing, of course, for just thermalization of standard classical statistical systems. So your fine-grained entropy is conserved if you just follow a quantum evolution. But you have fine-grained entropy 0 when you start from a pure state, which thermalizes, and a huge fine-grained entropy when you start from some mixed state that thermalizes. But after they have thermalized and emitted thermal radiation and so on, they're practically indistinguishable because the information is going to some very high correlation functions. Is the situation not similar here? Do you see any point of distinguishing states that have very different fine-grained entropies?
This is, I think, you're right, and when we look at quantum systems, we don't see any difference. And that's similar to the statement that if we stay outside from the black hole, we don't see much difference between cases where the interiors are connected or they are not connected, or that distinguishes between different kinds of interiors. The amazing thing about gravity is that the interior geometry seems depend on whether it's a macros, whether it's pure or not pure, and so on. So since you asked me this question about practical applications, so I'll mention one practical application.
different observables, for example.
Yes. So I like, well, I usually tell the story of Romeo and Juliet, and many of you have already heard this story. Maybe. Okay, so this, well, maybe I won't. I'll tell you a slightly different story. So, I'll tell you a science fiction story. So, imagine we had a universe like ours, but where dark matter consists of this weird 10 to the 25 massless fields with a charge U1. Okay, so this is just for technical reasons. But in this universe, you could have a black hole which is very big, and you could have two entangled black holes. And if they are entangled and the interior is connected, then you could jump into one black hole and come out of the other black hole. So you could use it for space travel. You could travel between two galaxies using these black holes. So this is, if you wish, some application of this notion of having an interior. So you can use it for
Real physics or just idealization?
the only thing that this follows from the standard rules of physics. This follows from standard rules of physics, assuming the nature of dark matter. I made this clear that something not about dark matter. I'm not the first one to discuss a huge number of dark matter fields. People have discussed it before. I think it's unrealistic. It's probably unlikely, but it is a universe that has this funny feature where. Now, I mentioned this, but even in the standard model, you could have little wormholes that connect the two black holes. So if you have very tiny microscopic black holes, you would have wormholes that connect them that are traversable of this kind. So I didn't have time to explain how you make wormholes traversable. They are sort of entangled but also interacting at the same time, but using in an important way the fact that they're entangled. So this is, let's say, one application of this. But I think something that I haven't discussed is that is the following. So much of this discussion was inspired by ADS-CFT and the connection between ADS-CFT and condensed matter. In fact, Ryu-Takayanagi is a condensed matter. Was a condensed matter physicist at the time that they wrote that paper, and he came from the condensed matter physics community, and he said, well, in condensed matter physics, and thinking about entropy and entanglement entropy was a useful notion for characterizing phases of condensed matter physics. And that's why he asked Takayanagi, and they collaborated and they developed this formula. And I think these connections to condensed matter have been useful in this whole development. I didn't review that, but that's been an important point. And it might be that in the future there might be practical applications that involve some of these concepts in developing better quantum computers and so on, in understanding the complex quantum state that the quantum computer contains in some way could be viewed as the black hole interior. So if you look at that complex quantum state in a coarse-grained way, you only see what we would call the exterior. But if you think about the full structure of that quantum state in the Hilbert space, that contains this interior in some way. So whether this is useful for thinking about quantum computation and so on is not completely clear.
Let me be more precise.
Because we are running out of, we are running over time. We will have a discussion session also towards the end, so I think that is, with all my respect, but I think it is a good time now to stop and postpone this discussion session because we have more speakers to go. So let's thank Juan again.